We'll start with the prayer. In the name of the Father, Son, Holy Spirit. Hail Mary, full of grace, the Lord is with thee. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners now and at the hour of our death. Amen. Father, Son, Holy Spirit. Amen. Great. All right. Wednesday, I think you guys got your course registration information for next year for current juniors / if you prefer, rising seniors.
All seniors rise up.
So let's take a moment and kind of talk about that. If you're a current senior, you ain't taking classes here anymore, so you don't need to worry about this. So current juniors, you guys have basically 4 options as far as a math class next year. By the way, the state of Michigan requires, as a graduation requirement, every senior takes a math class. So even if you've had 4 math credits to this at the end of junior year, you still got to take a math class senior year. Sorry. All right. First option, honors discrete math. Prereq for that is a B or better in both semesters of honors algebra 2. This is a course that runs on only even years, so this will be hasn't run in a while. This is a course that's basically would expect you coming in to have no knowledge of what we're doing in the course. It'd be everything that you need is going to be done inside the course, so you're not relying on things that you had done prior in your prior math courses. It's like all fresh and new. Traditionally, I'm the person who would be teaching this course. I would expect if it runs that would be the case again this year or next year. There is no like AP exam or like standardized test at the end of this, so there's no specific place we have to get to. It'll be largely just kind of based on what's going on with you guys. That's kind of how far we'll get. This class would be particularly useful if you're somebody that's interested, obviously, in mathematics or computer science or like a harder engineering, like an electrical engineering that's a little bit not as physical. But there's like a not insignificant proof component to this. But the neat part about the discrete mathematics is there's kind of like they're on a separate branch of mathematics from what you typically would do as a high school student. So you'd be exposed to things that like at no other point as a high schooler you would have the opportunity to get exposed to in mathematics. So like, and a lot of these things have obvious real world applications. So I think it's a really cool course in that regard. Another option is the math applications in personal finance. These are one semester courses each, typically paired together. Probably your most practical of any of the math courses we offer at Notre Dame, since the things that you'll do, particularly in the personal finance class, are something that every adult ends up doing. Like you'll talk about paying taxes and making a budget, financing automobile, and things like that. Also, probably the easiest easiest course option from a, like complexity standpoint. AP Calculus is probably the most difficult course on the list here. It's no joke. Your prereq is a B+ or higher in both semesters of this course. There is a AP exam at the end of the course that is required. So it's not easy. What I typically tell the students is the calculus part isn't hard. It's the algebra part that's the hard part. So like all of the little algebra rules and stuff that you've learned along the way come back, and you have to see kind of how to use them in maybe unexpected ways. Becomes kind of the trickiest piece. But yeah, it's again, excellent course. And then the fourth option is the IBSL course. Again, the prereq there is B or better in both semesters of this course. This course also has a standardized test at the end of it, the IB exam. So in this course, probably 50-ish% of it is like statistics, and the other 50% is kind of a grab bag of a variety of topics, some of which you'll have touched on in this course or your Algebra 2 course. And I don't think anything in here that you do is tremendously difficult. I wouldn't say any more difficult than the things we did in first or second semester of this course, but it moves pretty quick. So like, again, you can't kind of slack your way through that one either. It just, from the pace of it, it goes quite quickly. Any questions about these courses? If you change your mind and want to ask more about stuff, feel free to flag me down as it gets closer to the actual course selection dates. I'm happy to talk more about stuff. This is in the content library right now under course selection. So if you wanted to look at this stuff, it's all there in one place for you. Okie doke.
Thank you.
Sure. Today, let's start by taking a few minutes and answering some homework questions, if anybody has any, anyways. Mackenzie, is that a stretch or a hand? What's up? 6? Sure. Okay. So it says liquid is poured into a spherical container to height h. The radius of the sphere is 22. The top of the liquid is a circle with radius 10. Work out the height of the liquid h. So the trick here is using all the different ways you can draw a radius for a sphere. So the center of our sphere is like here. Any segment I draw to the surface of the sphere is a radius. In particular, this radius would be important because that's a part of the height that we're looking for, correct? The other part of the height is going to be this segment. I'm going to call that x. So the height is going to be 22 plus x, right? You agree with that? We just got to figure out what x is. There's another radius I can draw that would be quite useful. That one, which makes a right triangle as well. And then pretty easy to find x, and then h is just x plus 22. Is that cool, Mackenzie?
Okay. Oh, so you solved for it. Okay, got it.
Yep. Teague?
Sorry, how do you know that the 22 on the bottom is 22?
It's a radius of the sphere.
Oh,
So the center of the sphere is here. So any segment that you draw to the surface of the sphere from the center is a radius. And the radius is
yeah, I think
22.
about that in the 3D.
Yeah. So again, it's, you get stuck on the circle in the middle is the only place where I can draw a radius, but any segment going from the center of the sphere to its surface is a radii, or is a radius, excuse me. Amy?
So then you only need to solve for that one triangle. You don't do anything.
Nothing else matters. That's the only piece that you need is to get the x, so you can do 22 plus x. Yeah, no problem. So again, like mathematically, not difficult. Maybe a little tricky to see what you needed to do, or like, you know, geometrically tricky or whatever, to see like, oh yeah, all those things are radii all over the place. Anybody else? Questions from this? Ella? 4 is another sphere one, right? Yeah, so the same idea here. So again, if I picture this as a sphere, right? A is still the center of the sphere. So any segment I draw from the center of the sphere to the surface is a radius. So specifically, AC is a radius. And then that's a radius, right? So if we know the height of the water is 8, then the segment AB has to be 7. And then it's no problem finding BC. You're welcome. AB.
Wait, why?
Because the other part of the radius is 8, and 8 minus 15 is 7. I mean 15 minus 8, you know what I meant. Amy?
So, sorry.
It's okay. Jax?
It is 7.
Okay. So AF is the first thing it asks for. So the right triangle I would use in that case is just here, AEF. Since I know AE is 3 and I know EF is 5. Cool with that. And it says K is the midpoint over here. So we want the length of AK. Well, the triangle I would use there is AJK. And I know that either one of these, neither of these, I should say, look like right triangles. But I know since the base of the shed has to be a rectangle, that those are certainly have to be right angles at the corners there. So again, I know that JK, since K is the midpoint, is 1.5. Cool with that?
Yeah.
So I can, again, Pythagorean theorem there. And then the last piece, it says we want to figure out the height of AG and AH. So AG is this red one. So the triangle I would use here is AFG. Oops. And I know that FG is 2, and AF we found in part A. And then the other one I would do is AHK. And I know HK is 4.5. AK we found in part B. So we can use the Pythagorean theorem to get the AH. And then you just subtract them or whatever, whichever one's bigger. Probably pretty clear that AH is going to be the bigger one, just from looking at the picture, right? Okay. Anybody else with questions from here? Wowzer, that hurt. Okay. Let's go ahead and do the lecture, and then we'll finish the day out with our homework quiz. Sound good? That way we don't have to worry about rushing people to finish the homework quiz, so I make sure I have enough time to do the lesson. Okay. Section 9.3 is about angles within three-dimensional figures. So it's basically the same idea as 9.2, just instead of looking for segment lengths, we're looking for angle measures. But the same basic technique. So again, all throughout 9.3, my focus is going to be finding these calculation triangles and doing right triangle trigonometry inside of them. The thing that we need to be a little bit careful about, or make sure we really put on our geometric imagination about, is if I'm looking at the angle that's formed between a segment and a plane, really I'm talking about like some line that's inside the plane that's intersecting that segment, usually in the same plane as the segment. So like I just talk about the angle, I talk about the segment BC that's inside my plane, and the angle I'd be finding would be angle ABC, would be the angle formed between the segment AB and this plane. And this would be the same idea if we're talking about the angle between a segment and a face of the figure, right? So just to give a couple of examples of things you might be looking to do, if you want to find the angle between the base of the cone and a slant edge, we talk about like the angle B in this triangle ABC. Or if we're talking about the angle between the height of a pyramid and one of its edges, we'd be talking about the angle C within triangle ABC. Or if we want the angle between two diagonals, so that's going to be the angle, well, one of them's like an interior diagonal. Oh, I guess that's a diagonal on the face on the top. And then the other side of the triangle is a diagonal on the face on the bottom, right? So that angle would be this angle A here. So that's just an angle between two diagonals, where the one diagonal's on like the top of your ramp and the other diagonal's on like the base of the ramp, right? Maybe it's hard to see in 3 dimensions that that shape on the right is a ramp shaped. It looks like a doorstop. Do you see it now? Like a wedge. AF is on the top. It's going across the top of the wedge. And then AC is going on the bottom of the wedge. There's a diagonal across the bottom of the wedge. Again, you just have to, if you close your eyes and think about it in 3 dimensions, you can kind of see it a little bit better. Okay. So let's do a couple of examples, just kind of working through here. So here we have a triangular prism. Notice that you're given that the triangular faces are right triangles. See the little right angle mark there? We're going to start by finding the height of the segment EB, and then the length of the segment DB, and then the length of the segment DE, and then the angle that DE makes with the prism ABC. That's the pink angle there, angle BDE that's highlighted. Okay, so we'll start by finding the height of EB. The calculation triangle that I would use is the angle A, or is the triangle AEB. I notice given in my drawing is that angle A is 21 degrees. And I know this side is 15 because it's parallel to this one, or opposite, I guess I could say. And I'm looking for this side EB, so what am I going to use to do that? SOHCAHTOA. Which specific sine, cosine, or tangent am I using here? Tangent, because relative to the angle 21, the side I'm looking for is opposite, and the side I know is adjacent. So I just say tan 21 is equal to EB over 15. Solve for EB, get 5.76. Is everybody cool? Okay. Again, to remind you guys, I see lots of people writing things down. All these notes, all these PowerPoints are on My Notre Dame also, so don't feel like you got to write everything down because you have the PowerPoints, or you have access to all the PowerPoints. The next thing we're going to do is find this segment DB. So if I think about that, I know the base, or every face of a prism is a rectangle. So ABCD is a rectangle. So this is 15 and that's 23. So I can just do the Pythagorean theorem here to get dB. Cool with that? The third thing we asked for was dE. Notice that we have dB, we have EB, we're looking for dE. Well, that's just Pythagorean theorem time again, no biggie. Is that okay with you guys? Okay. And then the last piece, we're looking for this pink angle D. So again, I have my right triangle. I'm going to use the DB and BE as opposed to using DE. Not that it would be wrong to use DE, but if you think about it, to get DE, I used 2 rounded answers and then rounded that one. So there's like 2 levels of rounding in it, as opposed to each of these that are just have 1 level of rounding. So I'll get a slightly more accurate answer by using these 2 as opposed to using DE. Not that it matters for what we're really doing here. I don't think you'd notice a difference in a rounded to 2 decimal places, but this is Mr. Kulik's automatic math accurate mind going like, these 2 would be the better ones to use. So I figured I'd just make mention of why I didn't include the DE in my picture. Bless you. Okay, so relative to D, angle D. Or how do I find an angle inside of a right triangle? I use SOHCAHTOA and the inverse trig functions, right? Relative to angle D, I have opposite and adjacent, so I want to be using tangent. So tangent of the angle EDB is EB over DB. And to get that angle by itself, I do the tan inverse to both sides, and I type that in my calculator, I get 1184-ish. Everybody okay there? Reminder again, anytime you're looking for an angle measure, you're going to be using an inverse trig function, right? If you're looking for a side length from an angle, you're going to use a regular trig function. But if you're taking side lengths and turning them into angle measures, you're using the inverse trig functions. Let's do another example. Here we have a cylindrical drum that contains a stick that fits the diagonal exactly. If the radius of the drum is 5.8 and the height is 15.8, we want to figure out the length of the stick and then also the angle that the stick makes with the side of the drum. So, first thing, length of the stick. So I think it should be pretty obvious the triangle I need there is ACB, right? Now 15.8 is obvious, right? Where's the 11.6 coming from? Great. The diameter of the circle is 5.8 times 2. That's going to be the length of AC. So to find the length of the stick, I can just Pythagorean theorem that guy. Everybody's cool? Okay. The second question asked for the angle formed between the stick and the side of the drum. So what angle is that? Yeah, that would be angle ABC, right, between the stick and the side as opposed to the stick and the top. Or you'd find this angle, which is the stick and the side, as opposed to this angle would be the stick and the bottom. I'm going to find this angle ABC though, because I already had the triangle ABC drawn from the previous one. So I could just recycle my picture, which was easier for Mr. Kulik. So here, if we're looking for angle B and we have opposite and adjacent, we're going to be using tangent. So when I take the tangent inverse of both sides, I get about 36.29. Everybody okay with that? Again, are these questions really dissimilar from the previous set? Not really. We have to use an inverse trig function every once in a while, but like, whoop-de-dee-doo, it's still all right triangle trig, right? What's the hard part? Getting the little tiny sub picture that I need to solve. You know, the setup basically. One more example in this section. I bust out the fancy clip art for this one. Rescue helicopters hovering 156 meters above the sea. It is dark, and the helicopter is shining a light down onto the surface of the sea. If the diameter of the cone formed by the beam of light is 140 meters, what is the angle at the apex of the cone? So if I tried to do LMO as my calculation triangle, what's the issue there? It's not a right triangle. So I did LMN as my triangle. Where did the 70 come from? 140 divided by 2, so that was the diameter, so 70 is the radius. When I find angle M, what am I going to have to do with that? Because that's not the angle at the apex, right? Why am I just having to double it? How do I know that those are exactly the same, those two? The triangle is an isosceles triangle. Very good. So I know any altitude is also an angle bisector, and it bisects that opposite side. So this is true in all right cones, but it's due to the fact that the triangle LMO is an isosceles triangle. So again, tangent inverse of opposite over adjacent, and then I take that answer and multiply by 2. Everybody feel good? That was my last example for this section. Whoa! That was fast. It's okay, guys. It's basically the same thing we've been doing, right? Plus, I didn't have to draw the pictures this time, which, like, woof, that speeds things up, doesn't it? All right. The 9-4, we'll finish that guy up right here. 9-4 is about calculating volumes and surface areas. So the formulas that I'm going to be using in this section are whammo, all of these things. Ay caramba, Mr. Kulik. Do I have to memorize all this stuff? What do you guys think? No, man. No. So I'm just going to skate right past this. Is that okay? These are all on the formula sheet on the review, in the review pack on the last page. Okay. But again, you have this PowerPoint also if you want to look at that PowerPoint page where everything is grouped. All the area and surface area formulas all grouped together a little bit more sensibly than maybe they are on the review packet formula sheet. You know what I mean? Because it's all gridded out and stuff and columned and it's easy to track. Anyways, let's just kind of run through some examples. Basically what this comes down to is you might have to solve for some segments in order to use the formula involved, but you're basically just plugging things into the formula, right? Worst case scenario, you might have to solve for a piece that you need to plug into the formula, but like, you know, not a big deal. All right, 3 tennis balls are packed in a cylindrical container, just touching the sides, top, and bottom of the container. It means it's like all snugged up in there. The diameter of each tennis ball is 6.7. And then we were asked to do a bunch of things. Write down the internal height of the container, write down the diameter of the container, calculate the volume of the container. The curved surface is made of plastic and the top is made of metal. Calculate the area of the plastic, area of the metal. So tennis players in the room, when you buy tennis balls, what does it look like? You get 3 of them in a tube, right?
Yeah, it's the pipe looking thing.
Yeah. That's what's going on here. So if I want the height of the cylinder, the container, what's that going to be? Well, I'm going to stack 3 spheres in there, right? So it's just going to be the diameter of 3 of the spheres. Or about 20.1 centimeters. Everybody cool with that? I know that there's no extra space because it says it's touching the side, that those 3 balls are packed, touching the top, sides, and bottom. Okay, how about the diameter of the container? Same thing as the ball.
Sphere.
Everybody cool with that? So that was pretty easy, right? Had to use a little bit of imagination, but like, yeah, not that much imagination, just the right amount. All right. Part C then says calculate the volume of the container. So the container's a cylinder, so I know the volume is base area of the base times the height. The base is a circle, so it's pi r squared. How did I get the radius of being 3.35? 6.7 divided by 2. And the 20.1 we found was the height of the container already. So there's that. I guess I didn't round my answer to the nearest whole number like my instructions said. Oh, Mr. Kulik. So bad at following directions. Okay, it says the curved surface is made out of plastic. So like, you know, the cylinder part. And then the top and bottom are made out of metal. So if I want the area of plastic, I just need the lateral surface area for that cylinder. You remember we talked about that last time, is the area of the circumference of the cylinder, or of the circle, circumference of the base times the height. So since the base is a circle, that's 2 pi r times h. So I plugged in my values for r and h that I found previously. And I'm done. Not too bad. Everybody cool? The area of metal, so that metal is the top and the bottom. So I have the area for 2 circles. So 2 pi r squared. The r we found previously. Everybody cool? So not too bad. The hardest part was like getting the stacked tennis balls. You know what I mean? Okay. Next example. Suppose that we have a prism whose base is a regular hexagon, where the sides of that hexagon are 3.5, and then the length of the prism is 19. So something that looks kind of like this. When I say a regular hexagon, what does the term regular mean? Does that just mean that it like poops every day? No, Mr. Kulik. Hexagons are shapes. They don't have to go to the bathroom.
They're not living beings.
Yeah. What does regular mean? Means all the side lengths are the same and all the interior angle measures are the same. That's what regular means. I didn't think that pooping joke would make this much conversation, but I guess I was...
No, it's just like...
Yes, well, it's the end of the day, too, so everybody's got their giggle pants on.
I have a test to take after this in testing, so like, I'm going to have another class period kind of.
Gotcha.
Testing. And it's physics, so.
It's not trivial.
Yeah.
All right. Okay, so the first thing it wants us to do is calculate the volume of this prism. So I know the volume of a prism is the area of the base times the height. The base in this case is a regular hexagon. I don't have a formula for that. So that's going to be the trickiest part. The height is just 19, but we need to figure out the area of that base. So if I take my hexagon, I can divide it up into 6 isosceles triangles. Everybody's okay with that? So my plan is just going to be, I'm going to do 6 times the area of one of those triangles. Everybody cool with that? So the first thing I'm going to do is figure out the angle measure at the apex of one of these 6 isosceles triangles. So I know the whole way around is how many degrees? 360, right? If I go all the way around here, it's 360 degrees. So one of these apex angles has to be 1/6 of that. So I'll start by taking 360 divided by 6. And since these are isosceles triangles, I know the base angles are the same. So the remaining 120 degrees divided by 2. This turns out this triangle is not just isosceles, it's
Acute.
equilateral.
Equilateral.
Because they're all 60-degree angles. which is lovely, right?
It's all even.
So what does that mean this side length is?
3.5.
And this side length?
3.5.
So the easiest way to calculate the area for this triangle is going to be 1/2 AB sine C.
3.5 times 3.5 sine 60.
Drake?
And all the previous image before the triangle was like, this must be a hexagon, but I just see a wireframe cube. And it's
Oh, sure.
honestly freaking me out.
Yeah.
Oh, I see it now. Yeah.
Yeah.
Like I feel my
Nice. Good luck.
Yeah, you got me.
You got me too.
Oops. Okay. So we got the area of one triangle here, right? Everybody's cool? Notice that since this was not a right triangle, I didn't want to use 1/2 base times height. Everybody's okay with that? Let's say this wasn't an equilateral triangle, though. What if this was just a regular old isosceles triangle? What would I have to do?
That's the math.
I drop the altitude here, which bisects this angle and bisects this side. And then I can do the right triangle trig to get this side length.
Wait.
So I
Sorry.
drop this down. That splits this angle in
Oh,
half
okay.
and this side in half.
Right.
So it makes a right triangle over here
And then
that I can use to solve for that side length.
Yeah.
And then
just
plug
add-
into the same
I
formula.
see what you mean, because they would be the same. Makes
Yeah.
sense.
Or you could solve for this side length and do 1/2 base times height.
Okay.
That would be fine also.
Now if it was
Well, really 2 times 1/2 base times height, because you have,
now if it wasn't like
or use this base.
if the triangle wasn't like a size.
It has to be, if it's a regular figure.
Gotcha. So it'll always be
Yeah, I wouldn't give you like an octagon that's not regular.
okay.
That's rough. I'm not even sure what to do with that.
What if you just if you split it down the middle, would you just add that side and then do the same thing for the other side and add them together? Then you can
So you want to find the area of some trapezoid?
Yeah.
Maybe. It's not even guaranteed to be a trapezoid, I guess, because the sides don't even have to be perpendicular. Yeah, I don't know. It'd be tough. Anyways, continuing on. So we have the area of the hexagon, right, which is 6 times that area of the triangle. And then to get the volume of the prism, I just take that area of the base and multiply it by the length here. And there's my prism volume. Everybody's okay with that? These are pretty good PowerPoints though, right? Like,
Yeah, you did a good job.
I know.
I'm pretty impressed.
It took a long time.
It's paying off.
Yeah, thanks. Okay.
I'm really enjoying
The next piece was asking for the amount of material that I would need to build one of these pencil cases. So that's equivalent to just the surface area. So the surface area for a prism is going to be the area of both bases, plus the same number of rectangles that you have of sides on the base. So in this case, I have 2 hexagon areas and 6 rectangle areas. Everybody's okay with that? Since my hexagon was a regular figure, every one of those rectangles are going to be the same, right? Because they're all 3.5 by 19. Everybody's okay with that? So the area of the hexagon we found in the previous problem, right? We did 6 times 5.3. And to get the area of the rectangle, well, that's easy. 19 times 3.5. So I plug that stuff all in and I get 462 and change. Is everybody okay with that? Okay. Again, the hardest part for these surface areas is making sure you have the right formula. Since the surface area of a prism is going to depend on the shape of the base, we'll tell you the area of the base will change, the formula on that, and then how many rectangles you get is going to be dictated by the shape of the base. So there's not like a set formula for that kind of thing. It's just like, it's 2 bases plus a bunch of rectangles. The rectangles don't all need to be the same size though, right? If the base is not regular, then the rectangles will be different sized. It's kind of rough, but that's okay. you can always do the perimeter of the base times the height, and that'll give you all the rectangles. Okay. Last example question. We got a lampshade that's made out of a cone of glass and then has a glass hemisphere as the base. We're told the slant height of the cone is 29, so I drew that in. And the diameter of the hemisphere is 11, so I drew that in. Calculate the surface area of the lampshade. So the way this lamp is going to work is we're going to take this cone and we're going to set it right on top of this hemisphere so that this circular surface of the cone actually sets on the circular surface of the hemisphere so that neither one of those are actually surfaces. Did you guys kind of get that? So the surface area of the lamp is going to be the surface area of the cone without including the circle on the bottom, plus the surface area of the hemisphere, not including the circle at the top. Is everybody okay with that? So if you remember, the lateral surface area for a cone was pi RL. We talked about that last time. And then the surface area for a sphere was 4 pi r squared, so a hemisphere is just half of that. Oops. So where'd the 5.5 come from? That's the radius, so the 11 divided by 2. And then the L is just the slant height, which we have already, so that's 29. And so we just plug some stuff in. Everybody's okay with that? Again, the trickiest part was making the observation that you didn't need to include the circles part. The volume of the lamp then is going to be the volume of the cone plus the volume of the hemisphere. I don't need to make any adjustments here, because even though the one is sitting on top of the other and these circles at the bottom aren't surfaces, it's still containing the same amount of volume though, right? So the volume of a cone is 1/3 area of the base times the height. Since the base is a circle, that's pi r squared. The volume of a sphere is 4/3 pi r squared, or pi r cubed. But since we're dealing with a hemisphere, I just divide that to be by 2 to get 2/3 pi r cubed. And I just, the issue here is I don't have the height of the cone. But if I take this calculation triangle, I can use the Pythagorean theorem to find h. And then I can just plug it all in and add the stuff up. What do you guys think? Again, not super duper difficult. Probably the hardest part is like sorting out the calculation triangles to solve for the pieces that you need, or keeping straight what the letters mean in the formulas. But like operations wise, what are we doing here? We're adding, subtracting, multiplying, and dividing. We're not doing like any algebra at all. A little bit of right triangle trig here and there, but mostly just like plugging numbers into formulas. What do you guys think? Pretty good? All right. Let's do the homework quiz then, and then when you finish with that, you can start on the problem set. FYI, the problem set now you guys can do up through 31 or 32. That's going to be due the whole thing, 1 through 32, on next Sunday, not like the 20th, but the 27th, like the day before you get back from break. So no rush on that. In fact, it'd probably be better for you preparing for the test if you like wait and do a little bit of it during break some point so you don't get so far away from it. Okay.